Hello everyone, my name is Jonathan Villanueva and I will be presenting on the paper A Golden Age of Hardware Description Languages Applying Programming Language Techniques to Improve Design Productivity by Lenny Trung and Pat Hanrahan. This presentation is for the LV1 topic verification area with subtopic area design and verification languages. This paper talks about the introduction of new computer architecture emerging. There is a need for more efficient and expressive hardware descriptive languages to overcome the limitations of older traditional hardware descriptive languages. Older hardware descriptive languages like Verilog and VHDL were developed so long ago that they fall behind new modern programming concepts, which means they can be lacking in productivity and correctness. Hardware description languages were developed to describe, simulate, and synthesize digital circuits. The most common type of HDLs used are Verilog and VHDL, which are an industry standard today. Verilog was designed for digital modeling and for simulation. It uses syntax that is familiar to C code and is used for register transfer level design. VHDL was originally developed for the U.S. Department of Defense with the stronger type system as opposed to Verilog and is capable of offering better support for formal verification. VHDL and Verilog are considered low-level languages focusing on precise hardware behavior, and they lack modern programming functionality such as abstraction and modularity. Verilog semantics is based on module abstraction, similar to software languages. Its design compromises of hierarchical composed modules, simulation using data flow execution models. In this slide, we have an edge detector, FSM, shown in Verilog. This implementation was taken from the University of Washington, and it shows a two-input circuit with a one output design as a Mealy machine. The way the milling machine works is that the output is 1 if the current value of in is the inverse of the previous value of in. Some traditional some limitations in traditional hardware descriptive languages can be seen in low-level abstractions where design must be specified in terms of logic gates, registers, and clock cycles. They can be error-prone, introducing hardware bugs in product development, which can be costly to fix later. The traditional HDLs are also limited to code reuse and modularity, where they do not support very robust abstraction mechanisms, and reusing components requires manual duplication or very complex macros, which can lead to error-prone design. Traditional verification methods are simulation heavy, which is also very time consuming, and formal verification methods such as theorem proving or model checking can be difficult to integrate in existing HDLs. With recent advancements in computer architecture, such as domain-specific architectures like specialized chips for artificial intelligence, machine learning, networking, quantum computing, etc., there is a need for more specialized and efficient hardware. The authors mentioned that future HDLs should adopt techniques from programming languages to improve abstraction, correctness, and modularity. This paper introduces a multi-language approach to hardware design, where different languages can be used in different parts of the design process, giving them specialization in those areas. This approach is similar to how modern software development uses multiple languages and tools for better design, productivity, and correctness. The author suggests that different stages of hardware development should be using different languages optimized for that task. such as high-level language for abstract hardware design, a verification language for formal proofs, and a low-level synthesis language for optimizing circuit layouts. The Chisel A Scala-based HDL, as mentioned in the paper, is a hardware construction language that builds on functional programming concepts. The HDL generates Verilog code while also providing higher level abstractions than older HDLs. It also improves modularity and reusability, so larger scale hardware designs can be more manageable. Another example of the multi-language system discussed in this paper is the BlueSpec Handscale inspired HDL. This HDL uses rule-based programming and strong type systems to enforce correctness, simplifying hardware specifications while ensuring formal verification is integrated. Using a multi-language system approach for hardware development can benefit in many ways, such as allowing for higher productivity and better verification and reliability. Type systems that prevent design errors before synthesis. Formal methods, formal methods integration can ensure correctness at the specification level. Simulation and synthesis can be handled separately using dedicated tools. There's still some challenges when it comes to using multi-language hardware design systems that the paper discusses, such as getting industry to integrate these systems into their workflow. Processes have to be created to integrate new HDLs into existing workflows that rely on Verilog and VHDL. It costs money to branch out into something new and go away from using well-established tools. There are also challenges in ensuring that by using multiple languages, the systems will communicate uh, efficiently. Performance trade-offs has to also be considered at a case by case. More abstractions can lead to worse performance if not properly optimized. Future research is still required to optimize new HDL methods. Thank you for taking the time to watch my presentation, and I hope you have a great day.